Hi everyone, these are the notes for chapter 2.1 and 2.2 of your textbook, where we're going to cover atoms and valence electrons. We're going to review the structure of an atom, how to calculate different amounts of particles based on the information we have from a periodic table. And in addition to that, we're also going to learn about the organization of an atom and how that ultimately leads to a really critical property of them, which is the valence electrons, because that's going to actually lead to a lot of the chemical properties of what happens when atoms interact, and that chemical property is going to influence ultimately the molecules and how they interact in our bodies. And that's why we're really learning this nitty-gritty chemistry. So I know it might be a little bit of a grind, it might be a little bit difficult, but you really want to make sure you have a very firm understanding of the stuff that's being covered in this lecture, because if you don't get it down, it's going to influence your understanding of subsequent units, because we go back to this information all the time. Okay, so make sure you got it. And I really encourage you to look at your textbook after you take these notes, just to make sure you have a different perspective of how you understand this information. Okay, so this stuff is a little bit of a review. So in this case, this is just a review of the structure of an atom. So the nucleus is the center core of the atom. It's got protons and neutrons. The protons are positively charged. The neutrons are neutral, meaning there's no charge to them. All right. The proton typically characterizes the atom. We'll talk more about why that is later. But basically, if you have a carbon atom, the proton number is 6, and it will always be 6. The neutron number doesn't have to be 6, and it might shift around. The electron number doesn't have to be 6. It might shift around. But in order to be carbon, it has to have 6 protons. Neutrons provide the stability. It's basically because the protons are positively charged, and they don't want to hang out with one another. You need the neutrons there to keep some stability. I'll explain that in a little bit. Electrons are negatively charged, and they're really critical because they guide how atoms interact and the properties of the molecule. Ultimately, what influences chemical reactions, whether the water creates a chemical explosion with an element or doesn't mix with a certain element like water, it ultimately comes down to the way the electrons interact within a molecule. So pretty much almost all the stuff that we do, for example, salt by itself is an explosive in water, but the electron change in salt for the salt that we eat, and I shouldn't say salt, sodium element itself explodes in water if its electron numbers don't change. But if we shift the electron number, it becomes very stable, and then we can eat it. Okay, so the electrons are really critical for understanding how atoms and molecules act, and they orbit around the nucleus in circles. They're not like stable, they're not like static, they actually are constantly racing around. Okay? All right. Now, this is just a quick table summarizing some information about it. So the big thing here is just remember the charge of a proton is 1, is positive 1. The charge of an electron is negative 1. So they have equal strength of charges, but like in the opposite directions. One's positive, one's negative, while neutrons are neutral, 0. In terms of weight, the protons and neutrons are heavy. The electron is actually very light. So it's small, but it's powerful. So small, but negative, super negative. And of course, the protons and neutrons are found in the center nucleus, while the electrons are in the outside shells. All right, so a really cool key principle that's going to come up over and over again is the idea that opposite charges attract, meaning plus wants to hang out with minus, and minus hate each other. Plus and plus don't like each other. So like charges repel. So why do we have neutrons? Well, this is actually why the nucleus has to be it's very hard to change, because what happens is these two plus charges don't want to be nearby each other. So what keeps them together? Tons and tons and tons of energy. So actually most atoms, especially their nucleus, was formed by stars. And the energy of the star is what forces these protons by each other when they don't want to be by each other. They don't like each other. So this is very difficult, and it takes a lot of energy. So the more protons you shove into the center of an atom, the protons just really hate each other. So you need a neutral party, the neutrons, to be hanging out between them to keep them a little bit stable. Think of it as a friends group. If a couple people don't like each other, just letting them hang out by themselves is not a good idea. You want a lot of friends in your friend groups that kind of are chill with everyone else. Okay? And just another thing, plus likes minus. So why do the electrons not disappear instead and just hang out and try to stay nearby the nucleus? It's because the electrons are a little bit attracted to the protons, so it's going to help them hang out. This is also going to characterize stuff later on, because we're going to find out that the plus and minus ends of a molecule actually will eventually want to hang out with one another. And that's going to actually influence whether a protein makes a certain shape or not, because it's going to change its shape and bend and fold and stick to each other based on the positive and negative ends. Okay, so a big thing that defines an atom is its number of protons. We went over that. So an element is the atom, and it has that unique same number of protons. And just a heads up, this is the periodic table. It's a tool that's arranged by their atomic number, by their proton number. And actually turns out the way it's arranged means that the number of electrons in the outer shell is very predictable. All right, it actually has very cool types of or properties based on their location within the periodic table that are very predictive, and you'll have to memorize a lot of it in chemistry. All right, so here's some key things that you need to have for your notes. Write this down really quick if you don't already know it. So this is going to be needed in order for you to perform calculations on your worksheets later on, which is a key essential skill. So sometimes I'm going to ask you to give me the number of protons. What you're going to need is use your periodic table to find the atomic number. So I'll go over examples later. The second thing, the mass number, the weight of an atom that's provided on the periodic table, that one is actually the combination of neutrons and protons. Because remember, those are the two particles with the weight. Electrons don't have a lot of weight. They weigh very little, basically zero. Okay? So in that case, if I want the number of neutrons, I'm going to need to take the mass number and subtract the number of protons, aka the atomic mass, or the atomic number, sorry. Electrons are basically almost the same as the protons unless they're the ion. So if I have 6 protons, I can usually say there will be 6 electrons unless I am told that, oh wait, no, in this case it's an ion, and an ion is an exception where there's either less electrons or more electrons, because remember, in an atom you cannot change the number of protons, but you can change other particles. We'll talk about ions a little bit more later on, okay? So, but if you have a positive charge of an atom, remember the proton number is a base number. So let's say we have carbon, and that has 6 protons, 6 neutrons, and 6 electrons normally. In this case, if I have carbon 2+, that means it has 2 extra charges than it normally has. So in this case, the neutrons provide 0. Each proton provides a plus charge, so it's +6, and each electron provides a minus charge, so it's -6. In order for this carbon ion to be +2, what actually has to happen is it needs 2 more protons than electrons. So that actually means I'm going to need 4 electrons in order to achieve that +2. So that's why a plus charge means less electrons. Okay, and a minus charge actually means more electrons. So if I take that same carbon atom and make it 2- here, then in order to get -2, right, again, my proton number can't change. The only thing I can change is my electrons. So what adds to +6 in order to get -2? It is -8, which means I need 8 electrons in this case, okay, for this ion. So that's the idea of an ion. It's the shifting number of electrons to lead to that. All right, so this is all very complicated, but we're going to go over how to do this predictive math with predicting protons, neutrons, and electrons. So I'm throwing a lot of stuff at your head, but the easiest way to do it is for me to just show you examples of how to determine the number of protons, neutrons, and electrons in an atom. Now, really quick, I did not correct this. I'm going to review actually sodium and nitrogen. Okay? Okay, so a few things about the calculations. The top number you generally see on your periodic table is the atomic number, and then this decimal number you kind of see usually at the bottom or towards the bottom of your periodic table is what's called the relative atomic mass, also known as your mass number, the number of protons and neutrons added together, because remember, those are two particles with weight. Now, we're going to calculate the number of average hydrogen atoms, particles, the average sodium atoms, particles, and the average nitrogen atoms, particles. So now here's the biggest thing about the atomic number. So if you're ever unsure where the atomic number is on your periodic table, because sometimes it might be on the left, sometimes it might be on the right, sometimes it might be in the center, just make sure it's a whole number that's in sequence, meaning, it's in order. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? The mass number is not in sequence, but it usually is in increasing order, meaning that it's 1.008, 4.003, 6.941, 9.012, 10.811. So you see this increasing trend across the periodic table. So that is how you know that's the mass number. So again, mass number. Now, the mass number is always a decimal because it's the average weight of an atom across all the atoms that are known that are known in terms of their commonality on Earth. Okay? So in that case, there is no such thing as having a part proton or a part electron or a part neutron. So it's sort of like if someone says, hey, in my class, I have 12.011 students. That doesn't mean I have 12 students in my class and some students finger. It means that most of my classes have 12 students, and I might have one class in my school with 13 students. So that's why it's a decimal number representing an average. But when we're calculating a single atom, we want to use the whole number of the most common atom. Okay, so we're not going to use the number 12.011 for calculating the neutrons or protons. We're going to be using the nearest whole, 12, okay, which means it's the most common atom, also known as isotope. We'll talk about that in a little bit. Okay, so let me show you how to do the calculations for my average hydrogen atom, sodium atom, and nitrogen atom. So these are the atomic numbers and nearest whole number mass numbers that we're going to use for this particular, what we call isotope, for this particular atom that we're studying, meaning the most common, most average common hydrogen, sodium, and nitrogen atom. Okay, so I grabbed all of these from the periodic table entry that I have up here. Now, I'm going to calculate the proton. Proton number is super easy. It's going to be the atomic number, always. All right, so that's the number of protons. Now I'm going to calculate the electrons. Now, I have not been told this is an ion. So I have to assume it's a neutral atom, meaning the protons and electrons are normal, meaning that they are the equal numbers in order to achieve that neutral zero charge. So in this case, those are my electron numbers. Now this is where it gets a tiny bit more complicated. I need to determine the number of neutrons. So what I'm going to do is I'm going to take my mass number and I'm going to subtract it from my proton, or I'm going to subtract my proton number from the mass number. Because remember, the mass number is the total protons and neutrons together. So in this case here, my math will lead me to these number of neutrons because, right, I have one for mass number and one for atomic number or proton number. Same deal over here, same deal over here. So just a heads up, a lot of the time, especially for smaller atoms, the neutron number will actually often be the same as the proton number, but not always. So make sure you're doing that mass number minus the proton number or atomic number in order to get the neutrons. So this is a periodic table that we most often reference in our class. So just a heads up, the atomic number is here, the mass number is here. These numbers over on the corner here are called electronegativity numbers. That's going to come up in the next lesson on chapter 2.3. This is actually a number that indicates the strength of electron attractiveness, which is a fancy thing that makes no sense to you right now. Because first, before we learn about that, we have to understand valence electrons. All right, now, before we move on to valence electrons, though, I want to make sure we understand what happens if my normal atom, my most common atom, has a slightly different number of neutrons or a slightly different number of electrons. We talked about the electrons a little bit, but we're going to go a little bit more in depth. All right, so isotopes and ions are special terms for classes of atoms with different number of particles. Okay, so an isotope refers to an atom with mass number. Ooh, this definition is a little off. All right, so isotopes are atoms that are the same element, but they have different mass numbers. So in this case, that means that these are atoms with different numbers of neutrons. Okay, any atom where you know the number of neutron is an isotope. So even the most common, like hydrogen atom that we saw earlier with a mass number of 1, that's still considered an isotope of hydrogen. Just like a hydrogen with 1 neutron or a mass number of 2 is a different isotope of hydrogen. So it just refers to the atom of an element with a specific number of neutrons. Okay, so isotope, just an atom with a unique number of neutrons. Now, for the most part, there's not a lot different between most isotopes. Most isotopes are fairly stable, they act the same, they're chemically the same, they work the same in the molecule. The one exception are what's called radioisotopes. So radioisotopes are, for the most part, chemically similar to things, but there's something unique about them. Their nucleus is unstable, and over time, this nucleus of this atom, of a radioisotope, will break down and lose particles and change the number of protons they have. Or not necessarily protons, change the number of particles they have, which can include protons as well as other things. And this decay actually ends up releasing particles as radiation, and we can use the number of these radioisotopes found in an animal or in a person for different things, like medicine, or like doing carbon dating on a fossil to figure out how old it is. All right, a different type of atom with a different number of particles compared to other atoms of the same element. So let's talk about ions. So we covered ions a little bit earlier, but an ion is an atom or molecule that has gained or lost electrons, and that's going to result in an overall charge because they have a different number of electrons to protons, so they aren't neutral because they don't have that zero charge that is caused by the protons neutralizing or counteracting the electron charge. Now, because the proton numbers can't change, that fundamentally means that the electron number has changed. So that's pretty straightforward. The biggest thing with ions that we're going to get to in a little bit, though, is oftentimes these ions are common in instances where an atom has to gain or lose electrons in order to achieve stability. Okay, so a lot of our most common ions, like sodium, like calcium, these are ions that were formed because of the shift in their electron numbers in order to achieve something called a full valence shell, which we're going to learn about pretty much in a little bit. Now, these, by the way, I just wanted to show you how the symbol is determined for the ion. So in this case here, you see 6 neutrons, 6 protons, and 6 electrons. So I'm going to use a proton number to determine the element. In this case, it's carbon, because carbon has 6 as its atomic number. It's neutral because its protons equals its electrons. So I'm not going to write any symbol on this carbon atom because it's got a 0 charge. So me not writing a symbol here means it's because it has like an invisible 0 charge. Okay? Now, on the other hand, I have this atom for the negatively charged ion, and it's got 5 protons. That means it's not carbon. It is, in fact, boron. And now in this case, because I have one more electron than protons, I have one more negative charge than the positive charge, which means I have a charge of -1. Now, generally speaking, for a symbol, if I don't write a number, it means 1. So I will just write B minus, although in reality, you could also write B1 minus, okay? That's a really common way of writing the ion charge. If you have 2, though, you have to write the number. So, for instance, this is a really common ion. Oxygen would have 2 minus. Okay? All right. Now, down here on the positively charged ion, I have 6 protons and 5 electrons. So in this case, I have 1 more proton than electron, so I have 1 additional charge in the positive side. So it's still carbon because it has 5 protons, but in this case, it's carbon plus to represent 1 plus. But I could also write 1 plus if I wanted to. Most people leave off the 1 if it's only 1. So I'm going to give you example ions and isotopes for a given atom, okay? All right. So in terms of example of ions in this case, my hydrogen numbers, I know my base number of protons is 1, and as a result, I know I should have 1 electron. But in this case, because it's plus, it means I have 1 more proton than normal. So my proton is still 1, but I need to make sure it's 1 higher than my electron count. So my electron count in this case is 0. Okay? And by the way, my neutron number is still my mass number, 1 minus my proton number, 1. So my neutrons are 0. Okay? Over here for oxygen, it is normally 8. It's minus 2, so I need 2 more electrons than I normally have. So I normally would have 8 electrons, but in this case, because it's minus 2, I have 10 electrons. My neutron number is still my mass number, minus 8, so in this case, my neutron number is still 8. Fluorine over here, my proton number is always the same, 9, but in this case, it's minus, which means I have 1 more electron than I would normally have in a neutral atom. So instead of 9 electrons, I should have 10 electrons. And then my neutron count is just 19 minus 9, 10. Okay? Now, isotopes are just different mass numbers. So this has a hydrogen number of 1, hydrogen number of mass number of 2. So both hydrogen 1 and hydrogen 2, typo here, they're both isotopes. Oxygen 16, oxygen 15, they're both isotopes. Fluorine 19 and fluorine 18, they're both isotopes. I'm writing this number because these big numbers that come in after the name, that represents the mass number. But let me just write out all the particles so you can see the difference. So you can see here, the only number that's changing is the neutron number between the isotopes. Okay? All right, so now we're ready to move on to valence shells. So valence electrons are really critical because what happens is, in terms of molecules and how they're formed and ions and how they're formed, it's always going to be based on the idea that your atom is trying to achieve a filled outer electron shell. That is its most stable form. So valence electrons are the terms for the shell, the last shell surrounding the atom that has electrons on it, okay? If that outer shell that has electrons is at its maximum number of electrons, then your atom is at its happiest state. It is most stable. It is where it wants to be. So a given atom will react with another atom in order to achieve a full shell, and that's going to influence whether they make a chemical covalent bond, a permanent bond, or if they turn out to form an ion or whatever, or if it won't react at all. So in this atom over here for aluminum, it has a couple options. So we're going to learn that in terms of the shell model, the shell that is closest to the nucleus, so this is the nucleus here, that has a maximum of 2 electrons. The second shell, the next shell that surrounds it, has a maximum of 8 electrons that it's able to hold. And the third shell, for our purposes, has a maximum of 8 electrons. That's as far as we're going to go in biology. It actually is incredibly complicated, and that third shell, some stuff gets weird, but that's something you're going to learn in chemistry. For our purposes, we're just going to state for now that the third shell has a maximum of 8. Okay? Now, in this case, for aluminum, if this shell has a maximum of 8, I have a couple options. I can either add electrons to the shell to get it to 8. So what this means is this atom's going to need to do a lot of work to grab 5 extra electrons. Or it can dump electrons to get rid of that shell. What do I mean by that? I mean that it can get rid of these electrons and get rid of this whole shell. So it can dump 3 electrons. And now the last shell that has electrons is the second guy, and that one is full. So this aluminum can either, in order to achieve happiness, gain 5 electrons or lose 3. And in general, for atoms, it's going to do the thing that requires less effort. So this aluminum is most likely to form an ion by losing 3 electrons instead of gaining 5. So we're going to use this principle to draw the shell model for helium, oxygen, and sodium. In this case, when we draw shell models, it's all about the electron count. So we don't need to care about the neutrons. We don't need to care about the protons. What we're going to do is just pay attention to the electron number. So in this case, remember, unless I tell you that it's an ion, my electron number is the same as my atomic number or number of protons. So in this case, helium has 2, oxygen has 8, sodium has 11. And recall this electron pattern. So let's draw helium. So for helium here, I'll just do a thing to represent its nucleus, and now I'm going to draw the electrons around it. So in the first shell around the helium, I'm going to draw, it has 2 electrons. So I'm going to put 2 electrons on it. And look, I'm done. My shell is filled. I have the 2 maximum, so I am done with helium. It's also full, so for the first shell, so this helium, it is at its happiest state. It is stable. Oxygen, on the other hand, I have 8 electrons here. Okay, so 8 electrons, 2 electrons. This guy has 11 electrons. So in this case here, I'm going to start with my oxygen. All right, now let's add the electrons. So my first shell can only hold a maximum of 2 electrons. So now I need a second shell, so I'm going to draw a new ring around it. And now I'm going to add the remaining electrons on that shell. Now, generally speaking, it's a good idea to do them on corners, meaning that I'm going to draw my electrons in a pattern of 4 before I pair them up. So 1, 2, 3, 4. I have 6 electrons. I need 8, so I'm going to draw 2 more. So over here. So I have 2 electrons on this first ring, 6 electrons on the second ring. I didn't pair my electrons until I got to the, I did 4 by themselves before I paired them up. And this is my electron diagram for oxygen. Now, you don't have to pair them up like this the way I did. But if you get used to doing it in 4s, in 4 corners, before you add extra on each corner, this is going to help you prevent you from making bad habits that you take into chemistry. Because in chemistry, there's a reason for why I drew it this way. But you'll learn that in chemistry. Okay, let's go into sodium here. So sodium has a symbol of Na. That N got weird. All right, so just 2 electrons on this, full. 4 corners. That got full, so add another ring. And then put my last electron on the outside ring. And that's sodium. Okay? So in terms of drawing a shell model for an isotope versus an ion, these are slightly different because remember, the shell model is based on the number of electrons. So for this isotope of oxygen, which mass number of 15, my shell model is going to look exactly the same as a normal shell model for oxygen, meaning that it's got 8 protons, and so if it has 8 protons and it's neutral, it should also have 8 electrons. And I'm going to end up with a shell model that looks almost exactly like the other atom that we drew on the last slide. Done. All right. On the other hand here, oxygen with a charge of -2 is actually the most common ion that you're going to see for oxygen. And it has a different number of electrons. So recall, the proton number never changes. And it has a -2 charge because that means because the protons are +8, in order to get -2, I need 10 negative charges. So I need 10 electrons in order to achieve an overall net of -2, right? +8 -10. So then for my atom over here, I have my oxygen atom. And then for my nucleus, I have my 2 innermost electrons. And then for the ring surrounding it, I have 8 more electrons to add onto it. And that's my new oxygen atom, which is substantially different than my shell diagram for an isotope. Okay? So isotopes basically fundamentally look the same as any other atom in terms of the electron model, but for ions, they're going to look different. Also, a really cool thing, if you notice, this is the most common ion. Look at its shell. It's got the maximum number of electrons. And that actually is why this ion forms, because my atom wants to be stable. It wants to be happy, so it achieved that by getting 2 extra electrons to achieve that full shell. Now, if you didn't realize this, it turns out the periodic table is arranged in a way that shows you how many valence electrons are in the last shell. So if you look at the 2 columns on the far left of your periodic table, the first and second column actually have 1 valence electron and 2 valence electron in its outermost shell. And if you look at the 6 columns all the way to the right of the periodic table, they actually are in order of 3, 4, 5, 6, 7, 8 valence electrons. Okay? Or 2 if you're helium. Basically, this last column represents atoms that have complete full valence electron shells. This middle zone is weird, so we're going to ignore that in terms of valence electron shell prediction numbers. So just a heads up. So why do atoms interact? Well, those vacancies are really critical. Just like I said, elements will form ions or molecules in order to produce that stable outer electron shell, and that's because when there's no vacancies in the outermost atom, those atoms are the ones that are the most stable when the outside shell is completely full. If you have vacancies, then your atom is automatically going to be what's called chemically active. They're going to want to gain or lose electrons to achieve that filled shell. In fact, these atoms all here, which have filled shells, they're actually what's called chemically inert, and they don't react. So if you have a really explosive substance, they tend to be packed inside argon gas or neon gas or helium gas to prevent them from getting access to oxygen, which will cause them to explode. Because oxygen and airs, water, all those have the ability to react. Okay? So that's the basic idea, fundamental idea of how this works. Argon is a crazy stable because it's super full, but chlorine and sodium are actually only 1 away from being full. Chlorine needs 1 more, sodium wants to get rid of 1, so both of these, as a result, end up being really active when they're put out there in the world. Sodium, when mixed with water, explodes. Chlorine, when allowed out there in the world to react with other substances, will create very volatile gases, oftentimes, that produce a lot of heat as well in the reaction. So the idea here is atoms will gain or lose or share their electrons in order to achieve that happy, full, completed outer shell that's more stable. And it's going to allow it to influence what it interacts with. Ions, for instance, tend to form when an element gains or loses an electron in order to achieve that full outer shell. So this is a classic example. Oxygen is 2 away from perfect. Manganese, I think it's manganese. No, magnesium, sorry. Magnesium wants to get rid of 2 to get perfect. So magnesium is going to donate its 2 electrons to oxygen, and then oxygen is going to have 2 extra electrons. Magnesium is going to lose its outermost shell, and it's going to have 2 less electrons, and as a result, that's what allowed the ion to form. On the other hand here, my oxygen atoms here, these 2 oxygen atoms are going to now form bonds, and we'll go over how that works later on to achieve their full outer shell. In this case, they're going to share their electrons in order to get 8 on their outer shell. And you can see that here. 1, 2, 3, 4, 5, 6, 7, 8. So the influence of whether these 2 atoms end up producing ions or sharing electron is very much based on what those 2 atoms' wants are in terms of how it's going to achieve its outer electron shell. So the property of whether you get molecules or ions and what kind of bonds they produce are very much based on the valence shell. One last thing I want to mention, by the way, the normal neutral atom, oftentimes if this atom has an electron that's unpaired, meaning empty slots, it's going to be very unstable by itself, and it is going to have the ability or desire to want to interact with something else. And free radicals are actually very dangerous in our body, because what happens is, in their effort to get other electrons, they may pull that electron and create damage inside another molecule in your body, like your DNA or your proteins. So that's why people sometimes talk about free radicals in terms of health. So just a heads up, that's its significance, and free radicals might come up later on as we talk about photosynthesis in future units. So, key takeaways. We learned the particles in your atoms and in your elements. We made sure we understood that protons are always consistent across an element, which is why it's an atomic number. We also learned the difference between isotopes versus ions and how that alters the number of neutrons or protons in a given substance. And I shouldn't have said protons, neutrons or electrons in a given substance. Proton numbers never change. Okay? And on top of that, we learned that isotopes have a special form that can be used for science called radioisotopes that are a little bit less stable. We also understood and learned about valence electrons and their structure and how we predict where the valence electrons are and how much are needed to fill that outer shell, and how that ends up potentially influencing the atom in terms of how it interacts with its environment and with other elements. And we should have learned how to draw those valence shells, both for your normal atom as well as isotopes versus ion. Okay, that concludes our lesson. These are the vocabulary words that came up in our lecture. Make sure you understood them, and if there's any terms that you were unclear on, make sure to go back or even go into your textbook to make sure you understand it. All right? Good luck, and move on to any other work you have for the day. Bye.